this is a presentation about machine learning with Tidymodels. And Dr. Young said it already. He said, well, I didn't hear about Tidymodels, but I remember he wrote me an email once and mentioned the carrot package. And the author of the carrot package basically wrote Tidymodels in a drastically changed and improved way. Okay, well, let's start. I'm personally a big R fan and RStudio fan. I think it's a great software. So I just want to mention this presentation you are seeing is entirely done in RStudio. It can be presented over the internet, but it is entirely done in RStudio. That means that all the graphs you see, all the listings you see, are updated the moment when I start the presentation. So if I change something in the code, it will immediately be changed in the presentation, which is a huge advantage if you present something in R. Okay, let's start. The presentation has 4 parts, and I will make like a mental break after each part, and maybe we have a little bit time for discussion. If you have any questions where you don't understand something or something is not clear, or if Dr. Young thinks there is something not clear to the students, please interrupt me anytime and I can answer the questions. So the first part is a brief review of regression, and we will talk about the problem of overlearning. The second part will introduce the Tidymodels package, and it will show how easy it is to clean data, to start models, and to assess models. Then in part 3, I will introduce 3 connected machine learning models, the Lasso, the Rich, and the ElasticNet models. And I will use Tidymodels for it, and you will see how easy it is to start these models. And the last part is about cross-validation. There I'm pushing it a little bit. Cross-validation is extremely important when it comes to improving models by changing hyperparameters, and I will tell you later what that is. So these are the 4 parts. I made a learning guide and I will update it, and the updated version will always be available on this link here. Tiny URL, RTalk Tidymodels. And when the video is available from that learning guide, I will also link to that link. So let's start. What is overlearning and what can be done about this? This is what part 1 is about. So the goal of every machine learning procedure is to predict, and prediction means we predict data in the future, data we don't have at this point. Well, when we build the model, we only have old data. We have only data from the past. So the danger is, and that is called overlearning, that we build a model that very well approximates our data from the past, but when it is used to predict data in the future, it fails. And the goal of part 1 is to show you when overlearning occurs and to give you a little bit guidance on how to avoid it. Overlearning is a problem that is still not fully solved in machine learning. So when does overlearning happen with a higher likelihood? Well, one ingredient of the problem of overlearning is if we do not have a sufficient amount of data. This is often something we can't change. We have the amount of data we have. We can't create new data in many cases. Another ingredient for overlearning is if we have too many parameters. If our model has a lot of variables, or if our model is complex, we will have a lot of parameters to optimize. If we have neural networks and we have many variables, we end up easily with hundreds of parameters. And the last one is it occurs when the models are highly nonlinear. Very many or many of the machine learning models are highly nonlinear. So let's take a look. And what we do through this presentation here, we use a case study. I have housing data from Kings County or King County in Washington State. These data are collected between May 2014 and May 2015. There are sales of houses in this quarter. We have the sales price of every sold house. And we have some predictor variables like the square footage and some other ones. We will first only focus on the square footage and then later include other variables. We have a total of about 20,000 observations. That is certainly not considered few observations, but we will do a few modifications to trigger overlearning. We load the data here after we installed some libraries. The Tidymodels library, which includes part of the tidyverse. That's why I didn't install the tidyverse here. readr allows to read CSV files. And janitor is something that cleans up database names. If you have variable names in your data that have spaces or bars or other weird signs, janitor cleans it up. So what I'm doing here is I save my data in the variable data housing. Basically, a table will be saved there. I get them from the internet, and you can do too from here. And then I use the pipe command. I heard you're familiar with the pipe command, but at least I want to say what it is. The pipe command with this weird sign here, and that looks like a funnel here. What it does, it takes the output of the previous command, puts it in the little funnel, and pushes it to the next command as the first parameter. So this one reads the data. Now we have a data table. That data table goes here. So this becomes clean the data table, comma, and then the parameter upper camel. Now our data table is cleaned, and we rename the variable that is called square foot living, because it's a little long, simply to square feet. So now we have all our data in data housing, and I show you the first few records. Here are the prices, where the house is sold for, bedrooms, bathroom, square footage, the square footage of the lot, the floors, and a variable that is kind of weird because it doesn't have numbers. It has no if it's not at the waterfront, if the house is not at the waterfront. And it has a yes if it is at the waterfront. With this variable, as it is, we can't work because it's a nominal variable. It's not a numerical variable. We will come to that later, how to fix this. Before, let's look at the data we are using to create the model. These data are called training data. And in order to induce overlearning, we use only 0.1% from the data. That leaves us with 25 observations, which is obviously not a lot. The rest of the observations, we assume they are not known when we develop the model. These would be the data we use later when the model is in production to predict. We will use all these other data, the data that are not used, to see how well our model predicts or where are the problems. Here's the code. Our about 20,000 records are split into training records and into the data we want to use later to assess the quality. Here's a command. We use data housing, push it to the command initial split, and I will come back to that command later on. But you can here already see that the proportion is set to 0.001, and that results in that we only have 25 records in the training data set. We assign these records with the command training, put our split variable in here, and now we have a new data table, data train, that has only 25 records. And all the other records go into the table that is called data new. And we don't touch this one for now. We touch it later to see how good the quality is. These data new are filtered. We take out all the houses that are more expensive than 1.3 million. The reason for that is our training data, these 25 records, don't have any of these expensive and big houses. And it would be unfair to compare the quality of the training data later on a data range that was never used for training. So that's why we take these ones out. So at the end, we have a data set, data train we use to build our model. And we have data new that we want to use later on to see how well our model predicts. We will create two models, and they are called model 1 and model 2. This one is a univariate benchmark model. It has only one predictor variable, and it will not lead to overlearning. Model 2 will be designed in a way that we can see some overlearning. We start with our first model. Here's the equation for the model. We use square footage as the only predictor variable. It gets multiplied with the parameter beta 1, and beta 2 gets added. A very easy linear equation, which means our learning algorithm tries to find numerical values for beta 1 and beta 2 so that the error, the prediction error, is as small as possible. In this case, beta 1 and beta 2 can be calculated with the use of calculus. In other machine learning modules, the machine learning module would use what is called an optimizer and use a systematic trial and error mechanism to try different values for beta 1 and beta 2, try a lot of values systematically, improve the prediction quality step by step until we have a reasonable model. For you, it doesn't matter. We treat that as a black box. Our machine learning model finds the one or the other way suitable numbers for these beta parameters. And I will show you how. Our model will most likely not show overlearning because first, it's linear. It has only two parameters. The only thing would be that it has only 24 observations, but with this little parameters, it will not be a problem. So let's look at it. The way we do a linear regression, and you probably have seen that before, is we use the LM command, the LM function, linear model from R. And this function requires two things. It requires our prediction formula. And the way that is written here, it is, we have our dependent variable, our response variable, the variable we want to predict, separate with the tilde from all our predictor variables, the ones we use to predict. And we have only one, so that's why it is predict price with square feet. And of course, we have to tell R where to find the data. there in the data frame data train. What R does, it finds the right parameters, calculates a lot of other values, and stores these all in the variable, which is a very complex variable. It's called an object, model univar. So when we execute this variable, this command, we get the result. And the result here is that the best parameter for beta 1 is 231 approximately. The best one for the intercept is 65,537. So now I can substitute the betas with the numerical values, and I get an equation that has only the square footage, which means if I plug in any square footage, I get an estimate for the price of the house. And the variable price here has a little hat to show that this is an estimate. It's not the true house price, it's just an estimate. And I have a few examples here. Let's look at the first record. The square footage of that house is 21,070 square feet. If I plug that into this equation here, I get as a result, as an estimate, the predicted price about $567,000. Well, the price for what this house sold was $900,000. So we made an error. Most times we make an error, sometimes a bigger, sometimes a smaller. This is a bigger one. We underestimated by about $340,000. That's our error. If we want to see how good or how bad our prediction is overall, we obviously don't want to look just at one record. We want to look at all the records. So we could sum up all the records here and calculate the mean. The problem is that underestimates and overestimates would cancel each other out, and this is not what we want. So what we do, or what we could do as one option, is we record the absolute error, which is just the same than the error we recorded here, except every negative sign is switched to a positive sign, while a positive sign still stays positive. Now, if I calculate the error, the absolute error, over the whole column, I add them all up and divide by the number of records, I get the mean absolute error. That shows me how much, in average, I'm estimating incorrectly. Another way of doing this is, of getting rid of the negative sign, I square all my errors here. And if I get the average out of that, I would get the mean squared error. So we can do an estimate, and we can calculate the quality of our estimate. Here's a graphical presentation. The red dots are our data, and the blue line is our estimate. And you can see the distance here. If I, for example, here, this distance here shows me I made a small error. Here I made a tiny error, while here I made a quite big error. So what our machine learning or our regression is doing, it tries to put a straight line through these data to minimize these vertical lines, or to be correct, to minimize the square of these vertical lines. This is our model 1. Let's look at the second model. I want a model that is nonlinear, that has multiple variables. Instead of using new variables, I still stick to square feet, but I make it nonlinear by considering a second variable, square feet squared, a third one, square feet to the power of 3, and a fourth one, square feet to the power of 4. This model might lead to overlearning because it's nonlinear. It has several parameters to calibrate, beta 1 to beta 5. I have to admit 5 parameters in machine learning is really not what we would call a lot. But because we have only 25 records, this will already lead to overlearning. Let's look at it. First, we have to create our data set, our new training data set. And that is quite easy. I take the old training data set and I only consider the price and the square feet variable. So now my data set has only 2 columns. Then I add new variables. I add a variable square feet 2, which is the squared square feet 3 is the square feet to the power of 3, and so on. If I look at my new data set, here it is. You see it has everything that I need and nothing else. So I run my regression again. Here it is, my LM command. Price is the dependent variable, the response variable. And now you would expect that I list here square feet 2, square feet 3, and so on and so on. And they would be all separated with plus signs, which is to be interpreted as an and, not as a plus. But there's the easier way. I can just say, use all the variables that are in the data frame, obviously except the price variable. And the only thing what I have to do is, instead of having a long list, I just put a dot there. Still, I have to say where my data are. They are in data trained, which is modified now. And I get my result. Here are the coefficients for my variables. And here's my intercept. This leads me to an equation that means here, see 171 to the power of 3, 171 square feet, minus 149 square feet squared, minus this times square feet cubic, and so on and so on, plus 36,000 here. What is important about this equation is I can plug in square feet and I get an estimate. You see here, if you look at the p-values, that they seem all not to be significant, but let's not forget, we have one variable here in different powers, so we have a high degree of collinearity. We can really not interpret these p-values here. So let's see how well we did. I can do the same thing again. Here's my prediction. You see, it's a little bit higher than before. Here's my price. And here's my absolute error. Similar, that a little bit lower than before. And here's a graphical presentation, and that shows us why our prediction is better here. So our red line, that's our new model. Because it's nonlinear, it can bend. And this bending helps here to get these numbers a little bit bigger, a little bit better. See, it bends and catches these data better. It bends here downwards and gets these ones better. And it bends here upwards and gets these value better. This is the reason that our nonlinear model performs better than our linear one, which is shown in the blue line. But what if we now put all the data in there that we didn't know before? All these black spots are the rest of the data, about 20,000, that we didn't use for training. These would be the data that are used in production. And what we can see is, to predict these black data well, there is no need for our equation to bend up and down. It is actually counterproductive because it just bends down to catch these few data of the training data. So what it does, the red line predicts the training data well, but it does not predict future data very well. This is what is overlearning. The red model, although it seemed to be so good, is not a good model for production because it learns, sometimes we say it learns the data by heart and is not good in generalizing the underlying theory or the underlying law. If a model is flexible enough, a highly sophisticated neural network, you can actually predict the training data perfectly without any error. You can imagine a very flexible, complicated nonlinear function going through all these little dots. That is not helpful. That does damage when it goes to production. That is called overlearning, and that is what we have to avoid. That is a very, very common beginner mistake, to be happy about your model, how well it performs on your data, but it does not perform well on data it has never seen before. And I told you we can calculate the error. Let's start with the mean average error. It's calculated here. And let's look at the training data. If I look at the linear model and I look at the polynomial model, the nonlinear one, the polynomial model is doing so much better with the training data. But now if I look at the new data, the polynomial model is doing significantly worse. And we see the same thing, just with different numbers, when we look at the mean squared error. So that is the problem of overlearning. Well, we will talk about how we can predict how we can prevent overlearning later on. But before we prevent something, we have to have a way during our stage of developing the model to find out if overlearning is present or if it is not. We have to detect overlearning. How can we do that? Because we do not know the future data at this point. The trick is, from our training data, and of course, normally we have more than 25, let's say we have a few thousand, we take some of the data randomly away, somewhere about 15 to 30% of the data. We take them away, we withhold them, and we do not use them for training. Then when we are all done with our model development, before we release it for production, we check the quality of our model on these testing data, the ones we have withheld, to see if we have overlearning or not. If we don't have overlearning, we are good to go. If we do have overlearning, we go all the way back to square one. And here's how it is done. The easiest way is just a random process. We have 21,000 records, and we mix up the order of these records randomly. If they are sorted, let's say they're sorted by a house value, then if we cut off at the end, we would only cut off the expensive houses. So we randomly scramble them up. And then we take the last 15 to 30%, in this case, 6,400 records, and assign them to the testing data set. And only the training data are used to optimize our model. These data are used to optimize the model. These data are taboo. We cannot use them to optimize the model because we want to later on see and apply our model and see if we have overlearning or not. This is the first part, and I want to stop here for now before we go to the next part and see if you have any questions that I can answer. Everything clear so far? Good. The minimum, you get a deep breath. I put a lot of things, a lot of facts in this presentation, so I think it's probably good to have a little bit break. Okay, so now I will introduce Tidymodels. And before I do that, I want to tell you an anecdote that just recently happened. Max Kuhn is a big shot at our studio, and he developed this package. He's quite famous in the R community. And when I worked here on this presentation, I struggled with the Lasso regression. The Tidymodels did something which was not that clear to me, and from what I still believe, it is a small error, not a significant one. So I posted on the RStudio community, hoping that somebody else had a similar problem and could help. Within a day, I got an email from Max Kuhn himself. So these people care. It is like you have a problem with Word and you post something on the Microsoft site, and then you get an email from Bill Gates and say, hey, I can help you with this. This is actually what makes R a really, really nice program, that people feel a high responsibility, and there is not like a hierarchy. RStudio is a pretty flat, organized company. I thought I'd share that with you, and this way you also get a little bit of a mental break, and we can start now. So Tidymodels has more than these three parts, but these three parts I think are the most important ones, and these ones I want to cover. I will cover a fourth part at the end. One is called recipes, that is used to clean data and engineer data. We did data engineering. We had square feet, but we created a new variable, square feet squared. That is data engineering, and of course, I can do it in more complex ways. Then when I have my data, I use what is called the parsnip model that helps me to run machine learning models. Tidymodels doesn't have their own machine learning models. They use existing one. But my problem, until I would say 2-3 years ago when Tidymodel came on the market, was if I used a new machine learning procedure, it took me about 2 hours to figure out, just to get it started, how to get the data in there and get the first start of it. Because every machine learning model expected a little bit differently trimmed data. It had different commands. So you had to go for a long time through the documentation. Tidymodels provides a tool where you can call machine learning models in always exactly the same way. Then Tidymodels translates it to the specifics of the machine learning model and then calls the machine learning model for you, which is very, very convenient. And then finally, you didn't see the code, but you saw that calculating the metrics, the average, the mean average, the mean absolute error, or the mean squared error, it's not rocket science, but it's painful. You have to calculate the absolute value, you have to calculate sum, you have to calculate the mean. The metrics package makes this so much easier, and I will show that to you. Here's the equation we want to use. This time we use almost all of the variables. So we want to predict the price of our house. We use square feet times some number that our regression has to find. The number of bedrooms times a number, the number of bathrooms, the number of floors, the condition the house is in on a scale from 1 to 10, how much it is upgraded on a scale from 1 to 10, the square footage of the lot, the one of the basement, how good the view is, and our variable waterfront. Remember, that variable was coded in terms of yes and no. It was not a number. And calculating with yes and no's is not that easy. We have to do something. We have the year built and we have a constant here. And as you see, I don't want to show this to you in the presentation. I will show this part to you directly in the R code. So let's switch to R. You should be able to see my R screen now. And again, I load Tidymodels. And the other two packages, I read my data here. There's not much different, except that I now have more variables and I give them shorter names than they had at the beginning. Okay. I set my random number generator. So when I split the data, which is a random process, it is reproducible. And now I do my split, and I told you I will tell you a little bit more about it. So I split my data now in training data and in testing data. So the command for that is initial split, which requires obviously the data set. That's why I pipe it here as a first command, and some parameters. The first one is prop. It is a proportion of training data I want to get out of it. And if I set this one to 70%, then obviously my testing data will be 30% of the data. And then I have something here where I haven't talked about it. I mean, if I'm unlucky enough, a lot of the expensive houses, over proportionally many expensive houses, end up in the testing data set. And that might be the reason I get bad results on the testing data. That is not objective. So what I want is that the testing and the training data have similar records when it comes to the housing price. And this is what these two commands do. I strategize my random process by price. And the way I do it, I create 5 quantiles. The first one has the lowest price, 20% prices, then the second lowest 20% prices, and so on and so on. And the procedure makes sure that these 5 quantiles are approximately equally presented in the training and in the test data. You can do that manually if you don't use Tidymodels, but it is a real pain. Before you see, you have 10 or 15 lines of code. I use this one here, very easy to do. The King County data set is a very clean data set. Everything is in there. There are no holes, nothing. Well, I want to show you how you clean a data set. So I purposely sabotage the first 6 records of this data set. On the first record, I just delete the price and substitute with not available. Do the same thing on the second record. The third record, I sabotage the square footage. On records 5 and 6, I delete the bedrooms. And on record 7 and 8, I delete the lot of the square footage of the lot. And some of these records will end up in the training data set, and some of these sabotage records will end up in the testing data set. We can see it here if we look at the first 6 records of the training data set. See, the first one doesn't have a price. The second one doesn't have square footage. The third and the fourth one doesn't have the number of bedrooms, and so on and so on. And I want to reiterate that the waterfront here still has no's and yeses according if a house is at the waterfront, but we can't deal with that. So we have to repair, we have to clean all these problems. Well, what is easy to do and which was easy to do without Tidymodels, some of the record, if a record doesn't have a price for the house, I really don't want that record. I want to just throw it out. I can easily do that with or without Tidymodels, and I will show you. This record I don't want to throw out because it has a lot of other information. So, but I need something here for the square footage. One way I could do it, I could calculate the average of all the other houses, but that's some calculation. So I would have to say, calculate the mean of all the square footages and store that in the variable and make sure you don't consider records with an A. After I have that mean, I have to filter the whole data set for the NAs and substitute with this value. It's possible, it's not rocket science, but it takes at least 5 to 6 lines of code. Here, I have to substitute every no with a 0 and every yes with a 1. Not too much effort, but still some coding. Then I have a dummy variable, and that dummy variable can be used for regression. How do I do this in Tidymodels? In Tidymodels, I use a recipe. And the recipe is stored in a variable, but I first have to create it. So it starts with the command recipe, what a surprise. And I provide the formula here. It is important to point out that there is no modeling done here. I just provide some information about what is the response variable and which are the predictor variables. And only these variables will be considered in the recipe. So it filters out variables I don't want. And then I have to say which data I want to use, and I want to use the training data. That is the recipe command. Now, like every recipe, think about a cooking recipe, and that's the idea here, has several steps. Put 3 eggs in there. Knead the dough. Bake this, do that, and so on and so on. These are the steps here. So our first step, and every command starts with the word step underline, step dummy. It takes all nominal variables, so I don't even have to list them here, and makes them to dummy variables. Then I pipe the result to the next step, and I omit, remember, I don't want variables that don't even have a price. I omit every variables that have not a price. Now I go to square footage. Putting values in cells where I don't have a value is called imputation. And what I want to do here is I want to have the mean. That's why the command here, or the step, is called mean impute. Automatically calculates the mean for me and puts it in where it belongs. I could do the same for bedrooms, but then the records where I have my holes, they might end up with numbers like 3.12345 bedrooms. That's odd. So what I want to do here instead, I want to use the median for bedrooms. So the value that is not exceeded by 50% of the data, maybe 3 bedrooms, and I substitute it here. And this one I want to show you because this one is the one that I like best and use most. What this one does, it uses a machine learning algorithm to find an appropriate value for missing values. What it does, based on all the other values of that record that has problem, it finds the most similar, the nearest neighbor. And then from that most similar, it copies the value over to the one where we have a missing record. And you see here, I line up my recipe with pipe commands. And I have another step here, and you see that is commented out. I just want to briefly mention it. That step is called normalize. It basically brings all the data on one level. That is necessary, and it will be necessary is necessary for Lasso regression. In this case, it brings all the data to a level so that their standard deviation is 1 and their mean is 0. I don't need it here because I found out in the documentation of Lasso regression that Lasso regression does that internally. So I delete it here. Think about a recipe. This one is a recipe that is in the cookbook. Well, it's not executed. You have to execute, you have to prepare your recipe. So if you want a recipe to be prepared, you have to add the prep command at the end. There are sometimes reasons you don't want to have it prepared. You add the prep later on, but here we want to have it prepared. So I execute my recipe, and my recipe is now stored in the variable recipe multivariable OLS. You could have called it whatever you want. I like to call it recipe at the beginning, so I now know what it is. Now what I do, I bake my recipe. I use it. The bake command is very simple. It has the recipe name and the data it is applied to, my training data. And the result from that baking is assigned to the variable data train. Boom, done. I do the same for the testing data. One of you might think, wait a moment. When you calculate the mean and the median, and when you found the nearest neighbor, you were doing that based on the training data. But now you apply this recipe on the testing data. Should you not repeat the procedure first for the testing data? And the answer is no, under no circumstances. Why not? Because we said we do not want to use the testing data to analyze or to optimize our model. Otherwise, we might do exactly what we did before and we end up with overlearning. If we would have done that, the term for that is called data leakage, and it can lead to overlearning. That's why we don't do it. Let's look at our data. And I sort them a little bit nicer here. Look at the training data only. See, the first record is gone. It's deleted. The second record has now a square footage. That would be the average of all the other square footages. The second and third record that didn't have a bedroom number has now the bedroom number 3 because the median for the bedrooms is 3. And our square footage of the lot is substituted with the nearest neighbor values. Our data set is now nice and clear. And also our waterfront variables have now, instead of yes and no, zeros and ones. You don't see a 1 because none of these houses is at the waterfront, but there are houses at the waterfront. What you also can see, it is renamed. It's not called waterfront anymore. It's called waterfront automatically added underline yes. That reminds us that the coding is in a way that the yeses got a 1 and everything else got a 0. Okay, now it's time to run our model. We run our LM model. And that one needs a tiny little bit of introduction. What you were used to was a command that would look like this. That's all. LM, price, use the training data, and use as predictor variables all other variables you find. So it seems that Tidymodels made it more complicated. And objectively, yes, it is 2 lines more complicated. But the advantage is that this type of describing models will be used for all the machine learning models covered by the Tidymodels package. And these are a lot because Tidymodels, again, didn't develop these. They use existing ones, so it's relatively easy. So let's see what these 2 additional lines are. They're not too complicated. They need a model name, in this case, linear regression. You would find that in the documentation. And you have to tell the mode. The mode is either regression, and we have a regression here, or classification. That's it. That is true for all the machine learning models, so it's not too difficult. Then comes the set engine command. And the only thing what this one does, it says, where do I find the procedure I'm executing? Well, in this case, I find it in the LM package. And of course, there are many other packages for machine learning. So what I did with my LM before, when I had this one here, I do now with a little bit extended model. And at the end, I don't have LM, I have fit. Fit the model, and then I provide the same information, the formula and the data. That's it. I execute these 3 lines, and I'm done. And now I can look at my coefficients like I did before. Here they are. See? The square footage has 164 square feet. Bedrooms has 3,900. It's negative. That's surprising, but that happens in almost all of the real estate research. Think about if I have a house that has a given square footage, a given basement, a given amount of floors, and I add a bedroom, the house doesn't become bigger. It just becomes more divided. And if you assume, if you think about that, this equation is for the mean house. It means just if I have a mean house that has certain specifications and I add another bedroom, I make it more divided, I make that house worse rather than better. $3,900 worse. That's how the variable is to be interpreted. Let's look at the p-values. Small p-values show a low probability that these variables are actually 0. And they are all fairly low, extremely low, fairly low, fairly low, with one exception here. This one is a p-value of 0.70. So chances that this other, the basement variable, is actually 0 is about 70%. That is bad. What I would do here is I would run my regression again. And the only thing what I have to do, if I want to do that, I would go back to my models and I throw my variable out here. I would delete this variable here. And I run my regression again and run everything else again. No big deal. I can easily change my model. No other changes are required. I leave this bad apple in here for now. And you will see later on why I want to have one variable that is not that great in there. But again, normally I would throw it out. So I did my regression here. Looked at the parameters. Now I want to see how good my model is. Instead of calculating complicated formulas for the errors, what I do is I use the predict command that works on all the machine learning models covered in the Tidymodel. I provide the model name because this is where all the results, including my betas, are stored. And I say, well, use that equation that you just developed, including the betas, which are known numerical values, use the training data and get me predictions. I do that and I look at the predictions and here they are. They are oddly named .predict. And here are my predictions. The first house is predicted to be $434, $1,000 expensive, and so on. And second one, 438, and so on and so on. Well, I want to compare that with the training data because the training data include the true price. So what I do is I bind these two, my predictions that I just created, and the training data set together based on their columns. Let's run this command and look at it. Here are my training data like I had them before, but now see, I have my predictions. There is no need to calculate the error because the Tidymodel does that for me. The only thing what the Tidymodel needs, it needs a data frame, the one that I showed to you, that has the predictions and the true value in the order, first the true value and then the prediction. And if I execute that, it calculates everything that I need very conveniently to me, for me. And we can look at it. And I have here my mean average error. So in average, I'm about $137 off. It calculates our favorite, the R square, 64%. That's not bad. And it calculates also a value that is often calculated, but more difficult to interpret, the root of the mean square error. You can calculate other values. You just have to mention them here in the command matrix. You can add other values you want to be calculated. I did this here for the training data step by step. You can do that more effectively if you bind all the commands together with piping. First, you predict. The results from the predicting get connected with the testing data set. The results from that gets pushed to the matrix command. The truth is the price variable. The prediction is the .pred variable. And that's it. And if I have another model, I just copy and paste this command, adjust it a little bit, and that's it. Here are my prediction for the test data set. So maybe you try to remember that our original model had an error, a mean absolute error of 143,000 based on the testing data. That is more than on the training data, which is normal because it was never trained on these data, but it is not indicating excessive overlearning. Maybe a little bit, but not excessive. So can we improve this model? And the way we want to improve it is we want to make this model, because it has quite a few variables, we might want to make it a little less flexible. And that's where we use Lasso regression. Now I go back here to my slides. And we start part 3. And before I do that, I'm open for discussion, I'm open for questions, and I threaten you with telling you another boring story if you don't ask any questions. Anything you have not understood, anything that was not clear. We have some time. I want to give you a break, especially I want to give you a break to catch some air.
Yeah, I had a quick question about the imputing. So you would have to impute every variable that would have something like an NA in it, correct? Is that my understanding? Because I know with Python, I've done it. It kind of just automatically does it for all of them, but I think it usually just takes the means. This one, it looks like you could select median, KNN, things like that, but you had to do it for each variable, correct?
You can do it for each variable, like you said. If you want to do it for all, if you want to, for example, use the KNN impute for all, you can do that easily. You would just put in the command instead of the variable name. You would say, would put in all predictors.
Oh.
And that's all you have to do.
Oh, that's awesome.
The reason that I did it differently for each variable, I wanted to show off a few of the different procedures.
Okay, excellent. Thank you.
And the nice thing is you don't have to list it, because there are some terms you can just use, all nominals, all predictors, all response variables, and so on and so on. That makes it way easier.
Yeah, that does.
Any other questions?
Like we're doing prediction in machine learning, how much accuracy or dependency on accuracy or error we can think of, like, okay, this can give us this much amount of error as well, because as you mentioned, that it is overlearning as well. But if we are predicting, is there anything related to error which you want to share?
So, so the predictions, because I mean, here it's very obvious. Our model is basically a mathematical equation, right? And you plug in something into a mathematical equation. Even if you have a complicated neural network model, it is the same thing. You plug something in there into a mathematical formula. So when you talk about error, your prediction is as good as your computer is. And usually the predictions are good enough. So the error that comes from inaccuracy of a computer is so minimal that you can neglect it.
That sounds good.
And that is not only true for R, that is true for all other. So if you run, for example, a prediction on different platforms, you will get very, very similar answers. Probably not the same, but in the 15s or 20s digits, it might be different, but very, very similar.
So technically, error is that much lower side that we can definitely like overlook and go ahead with that. Correct.
Yes.
Answer.
If you do machine learning and you need to speed up your computer, you need a better computer, but you would not need a better computer to increase the precision. A normal laptop would just do it.
That answers my question. Thank you. I appreciate it.
Any other questions? Okay, so as a reward, I will not tell you another boring story. I will just go to part 3. So part 3 is I want to introduce rich Lasso and ElasticNet machine learning models, and that sounds like a lot, but because all 3 models are very similar, it is actually not a lot. And why I'm doing that is I want to show you how easy it is to do exactly what we did, just with a different model. Because in real life, you don't want to try one machine learning model. You want to try several machine learning models, maybe 3 or 2 or 4 or whatever. And you don't want to have so much work. You want to once clean your data and then run your models. And you can do that very, very easily with Tidymodels. So what is our goal here? Our goal is we want to make our model a little bit less flexible. Think about our overlearning. Remember the red flexible line? This is a linear line, but it is 12-dimensional, so it has some flexibility. So we want to take flexibility away from our model. And the reason we're doing that is we want to reduce overlearning if it is present. We want to get better results on our test data. See if we can do that. What is the strategy for that? The strategy we are using here is called regularization. It's a big word. Only thing what it does, it tries to make our parameters a little smaller than before. Think about if we have a little smaller parameter for beta 1 than before, then a change in square footage would not lead so much to a change of price. Thus, our model gets a little bit less sensitive, a little bit less flexible. We could just easily say shave the same amount off from all parameters, but that's not a good idea. Let's look at our bad apple here. If we shave off a little bit of this parameter, well, a change of square footage in the basement will not have a big impact, will have a smaller impact on price. Well, this was anyway not a very clear impact. So if we lower this parameter, we probably get rid of some noise. In an extreme case, and Lasso regression goes so far, it lowers the parameter unequally, and in some cases might even eliminate a parameter by setting it totally to 0. That is very specific with Lasso regression. And that's what we want to do. The question is, how do we tell our learning algorithm to do what we want? And here's a trick. Don't get scared from the formula. We look first only at this formula here. We have, here's our error. This is a predicted price for a record I, for the first or second record. I subtract the true price. So this is our error. This is nothing new. We did that before. And we square the error. So now it's our squared error. We add up all the errors. So we get the sum of squared errors. And what we tell our machine learning algorithm is choose the parameters beta to make that as minimal as possible. Okay. So what do we do with Lasso? With Lasso, we have the same term here. So nothing new. But we want to give Lasso an incentive to lower our betas. So that what we do here is we add up all our betas, but a negative beta is considered positive. So we add up the positive numbers of all our betas, and we add that to this arrow here. We have a penalty term. So we tell our machine learning model now, hey, try to minimize the error. That's one thing. But at the same time, I want you to minimize the penalty too. how much worse is the penalty and how much worse is the error? That is determined by this parameter lambda, and when we run it, we will set it to 540. Why 540? Because I did some tests and I found out 540 is a good value. That is not a very satisfying answer, but you have to stick with it for now. I will give you more later on. Can you see what we're doing here? We have nothing else than we had before. This and this is exactly the same. We add a penalty. And that makes our regression a lasso regression. And now the good message is, what is a rich regression? Same thing, almost. The only difference is, instead of using the absolute value for the penalty, we use the squared value. And obviously we have to use a smaller lambda because these values become big very fast. We want to use normalized values because you can imagine if we measure something in miles, our beta might be relatively low. If we measure something in feet, our beta is relatively high. So we have to normalize our values. But the good message is our procedure does that internally, automatically. We don't have to deal with it. One difference is obvious. If we have big betas, they get punished a lot here and not so much here. And another difference is, and that goes without proof here, that lasso regression tends to set bad apples to 0, while rich regression would set them only, the betas only to very small values. These are the differences between the two. Okay, then why don't we do it? Let's clean up first. And what we're doing is we do a lasso regression. You can imagine that a rich regression would work very similar, and I do it with you in R. So here's my lasso regression. Because there will be some randomness involved, I reset my random number generator. And now it really pays off that our commands are standardized. I want to run a lasso regression. This regression is in the GLMNet package. That's why I say set engine GLMNet. I would have to read the documentation from that package in order to find out how to run my regression. With Tidymodels, I don't. Like before, the first command is a model name and it's still a linear regression. The mode is not a classification, it's a regression. I add a little bit more information here. I want a penalty of 540. And I want a mixture that equals 1. Without further explanation at this point, if I set mixture to 1, I get a lasso regression. I will show that to you later why. And if you experiment around, I just want to give you, and that was the reason I asked on the R forum, I set the penalty to 540. For internal reasons, it really doesn't matter which penalty you choose, because GLM would always adjust your penalty. But let's ignore that. Just be warned, if you ever dig deep into it and you stumble over it, it cost me almost half a day to figure that out. Be warned, kind of remember it. But the penalty here is set to 540. We run our lasso regression. And of course, at the end, in order to execute, this is the same thing than the prep command for recipes. I have the fit command. and the fit command expects my formula, and it's still dependent variable is price, use all the other variables, and use the training data set. I execute that, and I'm done. And you see there's almost nothing different than before. The only difference is here a few more parameters, and I don't use the LM package, I use the GLMNet package, and that's a huge advantage of Tidymodels. I look at my coefficients, and what you would see, actually you can see it here. Let's look at a few of them. Square footage was 163, the original coefficient. Now, if I find it, oops. Oh, I'm sorry. I don't have the coefficients here. Here. These are the coefficient for square footage was, so for every square footage a house gets bigger, the price goes up by $164. These are the number of zeros. And now you can see the Lasso regression has a slightly smaller coefficient. But what is interesting, our bad apple variable here now is all set to 0. It's thrown out. We will later see that our Lasso regression did a little bit better. Let's look at the metrics. And again, now I just have to copy that, make a few changes, just change the model name. And here I have my predictions for the testing data. And if you remember the old result, I think it was 143. Our average error is a little bit smaller. So our Lasso regression indeed improved our results. Okay. So instead of showing you the rich regression, and you can imagine how much change that would be, almost no change. I would just change this value here to 0 and run it again. But I don't want to do that because you know what a rich regression is already. I want to show you an ElasticNet regression. And before I change the slides, please don't get scared to death. We'll get a monster formula. Here it is. But this is not a scary formula. It is not much new in there. Well, first of all, this part here is what we had in our simple, ordinary least square regression. That's nothing new. Now we don't have one penalty, we have two penalties. One penalty is the one we already know, right? And the second penalty is the penalty from the rich regression. The only difference is now we square our parameters and add them up, and here we take the absolute value and add them up. So instead of simply adding our two penalties, we take a weighted average. And you can see that. Remember, and I told you, I promised you I would show it to you, that the Lasso regression, when mixture is set to 0, when mixture is set to 1, we actually have a Lasso regression. Well, if this is a 1, then 1 minus mix is 0. If I multiply 0 with this arrow, it disappears. So if mix is 1, I have a Lasso regression like before. Well, if I set in another extreme case, if I set mix to 0, then his whole term here, the Lasso term, disappears. And I have a 0 here, so this becomes a 1. And I have a pure ridge regression. Does that make sense at this point? If not, then just simply interrupt me. Okay. Well, the obvious question is, what if I choose something in between? Let's say I choose mix (0.3), then this one would be 0.3. So the whole term would be 0.7. So my weighted penalty now is 70% of a ridge penalty and 30% of a lasso penalty. So an ElasticNet is basically a mix out of ridge and lasso. Well, one question is, how do I find the right lambda? Because before I just said it's 540, that's a little bit shortcut. And how do I find the right value, how to mix my penalties? My machine learning module will provide my betas for me after I have set my mix and my lambda. But that's all my machine learning model can do. So the only way is to find the right mix and the right lambda is to try. And in the old times, when I was still in Germany, that's more than 20 years ago, I was working with neural networks, and they had parameters like this. They are called hyperparameters because our model cannot optimize them. I, as a human, have to optimize them. What that meant for me, I was setting values for the neural network, but there was similar values in here, and I was running my model overnight. And the next morning, I would come and see how it did. And if I was not happy, I would do my work during the day. And before I left, I would start the computer again, another night, another result. Well, fortunately, now computers are faster, but the procedure is still the same. It's a trial and error process. The only difference is it's not like I have only one trial per night. To take 100 combinations of lambda and mix, you will see that takes only a very short time. And that's exactly what we will do now. We have one problem. How do we evaluate after we use a set of parameters, a combination of lambda and mix? How do we evaluate if our model is good or not? Well, you could say, well, no problem, we just use the testing data. No, we cannot use the testing data because the testing data are supposed to use only for the absolute finalized models. Otherwise, we get overlearning in our model again. So the testing data are taboo. What could we do? Well, we could do, because these data are taboo, we can't use them. What we could do, and please focus only on this part here for now. We could take our training data, these ones here, and cut off some of the data, same way than we did before, and make that our new testing data. And because new testing data is not a good word, we call them validation data. Then we use the rest of the data with our parameters and test how good that model does on the validation. And we would do that with the other parameters again and again, and this way we find the best model. There's one small problem here, and it's not too big of a problem, but we can make it better, is, well, maybe we are unlucky with our validation data. Maybe they do not really represent our regular data very well. So what we do instead is, instead of doing this only once, for each of the parameters, we have one set of lambda and mix. We run it with this one, and then we run it with this data set. And the only difference is that we picked a validation data set from a different section. And then we run it with the third one, different section, and with the fourth one, different section. So we build 1, 2, 3, 4 different data sets. We call them resamples, and run each parameter combination on each of these data sets. Then we calculate the mean square error or the mean average error here for this testing validation data set, for this validation data set, and so on, and for the last one. And to see how good our parameters do, we finally take the mean out of this. All this effort just for one parameter data set. How many resamples should we use? I used only 4 here to make it a little bit easier for the slide. Normally, you would use something between 5 and 10 resamples, depending on how many data we have. We have enough data, we can afford 10 resamples. But think about it. If I have, for my lambda, if I have 10 different values I want to test for my lambda, if I have 10 different values I want to test for my mix, I have already 100 combinations, 100 different models I want to test. I have to run them with each of these resamples, which is 1,000. So I have to run my model a total of 1,000 times. You can imagine how easily this goes up. If I had a third parameter I wanted to test, I have already 10,000. And that is where our computers get to their limits. We can handle this here still with a laptop, and I will run it for you in R. And if you want to program all this by hand, and you can do that, just to program these resamples, that would be so difficult to program. Again, it's not rocket science, but it would be very, very tedious. So what we do is we use, again, Tidymodels for that, and that's the last thing we do. And that is called cross-validation. Because again, randomness is involved when I build my faults. I set my random number generator, and I create my model again. And you see, nothing new. It's still a linear regression model. The mode is still regression. The penalty, I don't know. Instead of writing, I don't know, I write tune here. This is just a substitute for, I don't know yet. And I don't know the mixture either. And the engine is still GLMNet. So I define my model. And what you see here is there is no fit line. Of course, I can't fit a model if I don't know what the tune is and if I don't know what the mixture is. How should my machine learning algorithm calculate that model? So I omit the fit line here. And now I generate my parameters. I want a parameter for penalty and one for mixture. So I use the command parameters. and say one for penalty and some for mixture. And I say here the range for mixture should be between 0 and 1. We developed that. Actually, the default value, if I just leave this out here, it would still take a range from 0 to 1. I just want to show you if I don't want the default values, I can do that. The default values for penalty are between 0 and -1, and these are exponents. I leave it, I take the default values. So I have my parameters. Now I call that tune grid. I want the grid of parameters. That's very simple. And if you see the result, you will see how simple it is. Look, I want all the combinations between penalty and mixture. I have 11 values for penalty and 11 values for mixture. That gives me a total of 121 modules. And look here, I have a mixture of 0. And I have 11 models for that. A mixture of 0 means it's a complete rich model, but with 11 different penalties. Then I have one that has a weight of 0.1 between rich and Lasso. And at the end, here I have a Lasso model. So actually I have 11 parameter combinations for Lasso models with a very low penalty and with a higher penalty. And now I run all these 120 models against all the 10 different resample data sets. And that command is called tune grid, which basically means I run 1,121 different modules, 1,210 different models. So I defined my model already and saved it in the variable model multivariable ElasticNet. So I provide the model name. Now, because this module will actually be run 1,210 times, I have to provide a formula. Same formula, price, and the predictor variable is all the variables that in my data sets. And my data set is the training data set. I decided this is already stored here in the model variable. No, it's not. It's stored here. Now I create my folds. I want to have 10 different sets. Remember, in the graph, we had only 4. Here we have 10. Possibly, I could repeat that with different random numbers. Then I would have 20, 30, or 40. I don't want you to wait forever, so I have only one repeat. When I create my data sets, I stratify them again on price to make sure that the high and the low prices are kind of equally distributed over the different folds. And where are the parameters that I want to use? They are in the variable tune grid. Here it is. See, these are all the parameters. These are the 1,121 modules I want to use. And what do I want to minimize? I want to minimize the mean average error, so that needs to be reported. And this one just says, while you run, talk a little bit to me, show me on the console what you're doing. I run it, and here it goes. It works on the fold number 1, then on fold number 2, and so on and so on. And again, it runs a total of 1,210 different models. And for each of these models, it stores the mean average error. So because it's a mean out of the 10 folds, I will end up with 121 different results. And each result is basically the mean of 10 of my different resamples. I'm at number 5. And why it is working, I can tell you what I do next. The results here, my 121 results, together with a lot of other information, are stored in this variable, tune results. I called it that way. This is a pretty messy variable because it has a lot of information in it. And rather than searching forever for my mean average errors, there is a command in the Tidymodels that is called collect metrics that gives me a nice table that summarizes my results. And I'm at fault number 8. I could swear when I tested it, it went faster, but it probably didn't. And I'm at fault number 10, almost. So it's almost done. Saves the result in tune results, and I will collect what I want with this command and save it in my command metrics result from the whole grid. I do this. This goes pretty fast. Oops, made a mistake here. Here it is. And if I view this result, it becomes very clear what happened. Look, I have my 121 models again, and they differ because they have different values for penalty and for mixtures. And they were run against 10 different resamples. And the mean out of the first one is this one, 136. Second one was 137,000. This is the mean average error out of these 10 resamples. So if I want to find the best combination between penalty and mixture, I would just have to find the smallest value for here, and then I have my values, which is pretty easy, but I can automate it. I can say select the best ones, and I say, where do you find it? In tune results. Use the mean average error variable and spit out the best results. And here they are. The best model actually has a mixture of 0. That means it's a true rich model, no mixing, and it has a very small penalty. So these two parameters are now saved in the variable best hyperparameters. Now I have to do one last step. I want to use my best hyperparameters and run my model again, because this is the cool model I developed. How do I do that? There's a command in Tidymodels. It's called finalize models. You give the model that you have already specified, but remember, I only specified it. I didn't run it because I didn't have the tuning parameters set. But now I add the tuning parameters, so the model has everything that it needs. I add the best of all parameters, and now I can fit it. Use the price as a response variable, use all the other variables as predictor variables, and use the training data set. Run it. That goes very fast. It's done already. And now I did what I did before, and that's a nice thing. Copy and paste, change a few things. I want to see how well does it perform on my testing data. Here it is. Before I show that to you, let me clean up a little bit. So here's the performance on the testing data of my cross-validation model, where I used tuning to fine-tune my hyperparameters. The average, the mean absolute error is now 141,000 based on the test data. And I still have the other data here. This is the one from Lasso. This is the one from OLS, hopefully. Yeah. Nope. Here's the OLS one. So this one is the OLS one. Look, the mean absolute error was 143,000. So my estimates were about $143,000 off. That's not so bad if I don't even see the house. If it's just from my desk, then the Lasso model improved it to 142,000. And the ElasticNet model, where I fine-tuned my parameters, my hyperparameters with cross-validation, improved it to 141,000. To be honest with you, this is a small improvement, and I can tell you why. Because remember, we had 12 variables, but our data set was 20,000 observations. So overlearning was really not a problem. It was more to show you the procedures here. But again, we have a slight improvement. It's just not very big. So what did we learn? Or what you hopefully learned is how to build a model with Tidymodels. And we used the simple ordinary least square models. We did cleaning. We built the model. And we used the metrics from the yardstick package. We used the metrics from the yardstick package to assess the data. That was the first one. We also learned what overlearning is. That was actually the first one. We built Lasso, Rich, and ElasticNet models with Tidymodels. And the little bit more or lot more sophisticated part was how to tune hyperparameters. If you just got the rough idea of it, that is good enough. And you always can go back to the video and review that part. And then I think a lot of things will become much more clear. Fine-tuning of hyperparameters is something you have to do when you do machine learning. There's no way around it. But it is a little bit abstract. You have to look at it a lot of time until it becomes kind of second nature.